Alrighty, so today, post-assessment, we are definitely going to be going over relatively new concept. So far, what we've been doing is we've covered congruent triangles, we've covered what congruent means, we've addressed that it basically means that they are exact copies of each other, that it's a similarity, but it's an extra step up from similarity. Um, so just about the same time, so about the same time in the similarity unit that so basically about the same time in the similarity unit that we are now, we started looking at ways to prove similarity, ways to show that triangles were similar to one another. So this time, today, we are going to be talking about triangle congruency and ways that we can prove triangle congruence. Unfortunately, this is going to be a lot of vocabulary. This is going to be a lot of concepts. So, like I said, it's going to be one of those things where you're just going to have to remember it. You're just going to have to memorize it. If anybody tends to remember something, I'm going to adjust the lights here. If anybody tends to remember anything from geometry, it's always things like side, angle, side, angle, side, side, side. That's from this. That's from the unit that you are, that's from the unit and the part of the unit that we're going over right now. That's what we're going to start right now. So, I mean, I guess you can get excited about that what you're learning now is probably going to be what you remember about geometry every day for the rest of your life. Well, probably not every day, just when like someone reminds you of geometry and you have all those like those silent war film Vietnam flashbacks of the black and white film and the screaming and the napalm, and then you'll remember side angle, side, 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 side. You won't remember how well you did with the transformation test. You won't remember that. You'll just remember congruence. So let's go ahead and get those memories started. Um, Determining triangle congruence. We're going to go one theory at a time, one theorem at a time. So we're going to start with the side, side, side congruence theorem. Some of these are going to sound really intuitive. They're going to sound really simple, really obvious. It's going to be like, Mr. Foster, Professor Foster, why are we going through this? Why can't we just assume this? Why isn't it, why can't, yeah, I mean, basically, why can't we just assume this? Why can't we just move forward with this as a trivial explanation the way that you did with algebra and math? Hang on, I'm going to fix this here. Okay. Basically, the answer is I don't really have an answer. It's yeah. Basically, congruency is different from similarity. There are going to be some parallels, no pun intended. There are going to be some parallels between congruency and similarity, but congruence is as I mentioned before, it's a higher degree of similarity. You have more things in common with congruence than you do with similarity. As I mentioned before, congruence basically means that the two triangles or the two shapes, well, I mean, let's stick with triangles. The two triangles that you're looking at are essentially just copy paste versions of each other, one on top of the other. If they're similar, and I'm recording this as we're working through the similarity unit, if they're similar, it means that the angles are equal, but the sides aren't necessarily so. If they're similar, then they're kind of like what we did with the transformation unit, where we had dilation. The shape itself was basically the same, but the sides would change, but the sides would be a different length. They'd be the same proportionate length, and so that was where we had things like scale factors, and we had to scale things up or scale things down based on what k was during the transformation unit. And with similarity, carrying on from that with similarity, um, you could have triangles that had one of the characteristics of similarity is that you had triangles that were you had triangles that were had the same angles but had different side lengths, and so they'd be similar because they'd be more or less the same. They'd be more or less congruent to one another. They'd be the same triangle were it not for the fact that they had their sides were proportionately different. With congruence, there isn't that. With congruence, there isn't that. With congruence, the sides are the same measurement. Um, with congruence, the angles are also going to be the same measurement or relative measurement. Does that mean that you can use angles just to determine congruence? No, we'll get to that later. But yeah, with congruence, like I said, like I keep saying, congruence is just a higher level of similarity because it has to involve the physical size of the involves the physical size of the shape as well. So let's take a look. All right, start out with side, side, side. If three sides of one triangle are congruent to three sides of another triangle, then the two triangles are congruent. So if you have AB equals DE, let's see, if AB equals DE, here we go. I'll even do it on camera here. If BC equals EF, and if AC equals DF, then triangle ABC is congruent. That's with the little equal sign with like the little hair flip, is congruent to DEF. And just like with similarity statements, this congruency statement, you have to refer to this. You have to refer to the you have to make sure that the angle references are also the same. So angle A has to refer to angle D, angle B has to refer to angle E, and so on. Also, side AB has to refer to side DE, so thankfully that one does. BC has to refer to EF, so yeah, we're in good shape there. So let's see, determine if the triangles are congruent. Let's see, are the triangles congruent here? Well, um, let's take a look here. I've got, well, I'm trying to see if that, I'm trying to see, so you see, here's the thing, it's a mirror image of it. I know that it's a mirror image of it, but my issue is that reflections aren't necessarily congruent. So that's kind of my problem with this. Is you know what? I'm overthinking this. This is the side congruence theorem section. So are the three sides of the triangle congruent? Let's see. Are there three sides of both triangles that are congruent to each other? Well, based on the hash marks, NO is congruent to NQ. Let's see. OP is congruent to QP. And then NP is congruent to NP, which is technically a trivial statement, but when you're writing out proofs, it always helps things out. So yes, they are congruent. What is the congruency statement? I'm going to say triangle NOP is congruent to triangle NQP by side, side, side. And so that's how you would struggle. So when we're talking about being able to prove things or proving things in geometry or in geometry class, this is what we're talking about. You have a picture and you have information within that picture. And so I'm saying that NO is equal to NQ. So we know that, so these two are equal. So I say NO equals NQ, I write it down over here. I know that QP equals OP because that's what it's labeled here. So I write it down here. And then obviously NP is equal to NP, so I write it down here. Since I've established these three facts all the way over here, I can say that they are congruent because of the side, side, side congruence theorem. which is, again, if three sides of one triangle are congruent to three sides of another triangle, then they are congruent. So there we are. This is a structure of what is going to be called a proof, which we will get into next year or next semester, however you want to call it. And so it's basically putting forward information in a sequence, in a logical sequence, so that we can draw a conclusion from it. It's like, so I'm saying NO is equal to NQ. I'm saying OP is equal to QP. And I'm saying that NP is equal to NP. And so by saying all three of those things, I am now saying that I have two triangles that have three sides each that are equal to each other. Therefore, by the side-side-side congruence theorem, these two are congruent. I don't know why I'm hanging out on this one as long. We are going to have plenty to work with, so let's move on to the next one. All right, let's see. Determine if the triangles are congruent. Well, I like their odds, but let's get started. Let's see. I've got JK is congruent to ML. Alrighty, because of the little marks here. Then I've got KL is congruent to JM. Alrighty. And then again, I've got KM is congruent to KM. So one of the questions I'm sure you've asked is, if I've got a shared side like this, do I have to list it as part of the proof? Technically, yes. Some instructors will say, no, you don't have to. But here's the thing. If we're going to teach you how to write proofs, we're going to teach you how to write proofs the right way. And if we're going to teach you how to write proofs the right way, we're going to teach you to write proofs up to the academic standard that is expected of proof writing. And what that means is, even if it is a trivial statement, you have to include it. And so if you just said JK is congruent to ML, which it absolutely is, and KL is equal to JM, which it absolutely is, and you said based on that it is, and they said based on that it is congruent, then your proof would be incomplete. They are congruent by the side-side-side congruence theorem. Your proof would be incomplete because the idea is that someone should be able to read your proof and follow your logic all the way through, absent this drawing. The drawing should be part of it, and the drawing should help. But if your logic can't withstand, but if your argument is poorly constructed, that it needs the drawing, then your proof isn't very good. Then your proof writing skills aren't up to par. So yes, even though it is a trivial statement, even though it is obvious that Km equals Km, you do have to include it. So are they congruent? Yes, and I'm so happy. So the congruency statement, I'm going to say KJM is congruent to triangle, and then I went, so MLK, there we go. And there we go. Oh, I forgot, by side, because I proved that they are congruent by pointing out that all three of their respective sides are congruent to each other. All right, now our next theorem is the side angle side theorem. So we had the same thing here with similar triangles. If two sides and the included angle of one triangle is congruent to two sides and the included angle of another triangle, then the two triangles are congruent. The difference between this one and the similarity is that when we were dealing with the similar triangles, the angles were equal because angles in similar triangles have to be equal, but the sides just had to be proportional. And so the sides didn't have to be equal, but they had to scale up according to the same scale factor in order for the triangles to be similar. Here's the thing though, in order to be congruent, the sides have to be congruent to one another now. And so if they're proportional, then they are similar. If they're congruent, now they're congruent. And another very key important detail is that the angle So you're doing side angle side, so there has to be an angle there. The angle has to be between the two sides. So again, this isn't different from the side angle side theorem that we used with triangle similarity in the previous unit. It's just that now, instead of being proportional, the sides are equal. So let's see, if, oh, here we go. If AB is congruent to DE, if angle B is congruent to angle E, and if BC is congruent to EF, then triangle ABC is congruent to triangle DEF. And so that is how, and so that's how, well, I mean, that's also how you would write a theorem, but I really, nothing against you all, but I don't expect you to be writing any geometric theorems from the work that we're going to be doing. But that's how we would fill it in. That's how we would expect it. All right. So now we're going to do another pseudo proof. We're going to be doing another pseudo proof by verifying that the angles, that the triangles are congruent. So are the triangles congruent? Well, we've got the two sides that are equal to each other. So we've got two sides that are equal to each other. So we'll document that. I've got BC is congruent to CD because that's what we're given. I've got CA is congruent to CE. Now I need to have the angle. The only angle that's between these two is obviously angle C. The good news is I know for a fact that these two angles are equal to each other. The reason that I know that those two angles are equal to each other is because they are vertical angles. For those of you that have been in my class long enough, you know that vertical angles are my absolute favorite types of angles because they are always equal. Vertical angles are formed when two lines intersect one another. And so they share a common vertex, but they don't share a side. So the angles that are formed that share the vertex but don't share the side, those angles are always equal. So that means angle, I'm going to have to be a bit more specific, BCA is congruent to angle DCE. Oops. So because I've named all three, so I've listed as part of my proof all three of the criteria necessary. I've listed three criteria that are 100% true and provably true looking at the diagram. I can take any one of these statements and say, see, according to this diagram, these are true. All right. So are they congruent? Yes. Congruency statement. I'm going to say CBA, triangle CBA is congruent to triangle CDE by side angle side. And that would be all I would need to list the proof and consider the statement proven. All right, next. I don't know why I went exceptionally slow with that one. Oh, okay, here we go. Determine if the triangles are congruent. So, yeah, okay, this is a good one. Actually, I could probably prove that G, J, and HI are parallel, but one thing at a time, one thing at a time. So we're trying to prove that the triangles are congruent. We're probably going to use the side angle side theorem because that's the theorem that we're at. So determine if the angles are congruent. Well, I see first of all that side GH, oops, is equal to is congruent to IJ. I caught myself there. I also see that angle H is equal to angle J because that's what the little loop here means. It doesn't just Usually when I use a loop, whenever I'm showing similarity or congruence, it's to make a reference or to say that it's to make a reference to a specific angle. The reason I do that also is to say that this angle is equal to this angle or this angle is equal to that angle. So I'm not just highlighting reference angles, which I absolutely am, but I'm also saying that this angle is equal to this angle is equal to this angle. And so this notation says that angle H is equal to angle J. And I talked so much smack and then I just said it. So is congruent to angle J. So now, again, just like we had before, I've got a side, I've got an angle. I just need one more side, and the side that I'm going to say is equal to each side is their shared side. They have a shared side of HJ. So again, HJ is congruent to HJ because it is. And again, it seems like a trivial statement. It seems like a silly observation, but it is a true statement that you must include as part of your proof. So, oops, are they congruent? Yes. Congruency statement. I'm going to say triangle GH, oops, GHJ is congruent to IJH by side angle side theorem. And again, I start out with if I'm going to prove it using side angle side theorem, then I have to have a statement of two sides, and then I have to have two sides, and then the angle between them in order to show that these two triangles are congruent. Now, with this one over here, I started out with two sides, and then I went to the angle. Do I have to do side angle side in order for the proof to be right or correct or whatever? No. As long as in total you have two sides, as long as you have the correct components in the correct positions. So it doesn't matter what order you refer to them in, it doesn't matter what order you list them in over here. As long as you have all three of these somewhere in whatever order, you can still make the statement that you are congruent by side angle side. So over here, I would say this is more of an ideal proof because I've got one side, I've got an angle, and then I've got the second side, and then I'm using side angle side. But are you going to lose points? Are you going to be docked by grading if you don't include it in a direct thing? No, you're not. You're just not. So don't worry about it. All right. As an extension of side angle side, we have angle side angle. So if two angles and the included side of one of the triangles are congruent to the other angles in the triangle, then the two triangles are congruent. So we're going to go over here and we're going to do the same thing with this theorem and the next two theorems. Yeah, two theorems. And two theorems, yeah. Then we're going to call it a day. So angle side angle congruence theorem. So if angle A is congruent to angle D, I'll stop it at some point. If AB is congruent to DE, and if angle B is congruent to angle E, then triangle ABC is congruent to triangle DEF. I think at this point we can just assume that anything labeled ABC is going to be congruent to DEF, but one thing at a time, I suppose. So let's get to some examples where we can see if things are congruent or not. So starting here, again, this is angle side angle. I'm more saying that for myself at this point. All right, so I see an angle side and an angle here. So again, following the notation, I see that angle B and angle E are equal to each other. Man, are congruent to each other. Well, no, they are equal to each other. That's exactly what the notation means. They're not congruent to each other. They are equal to each other. Angles can be equal to each other. The measurement of angles is equal. It's the sides that are, you know what, never mind. Let's see. The sides BC and CE are congruent to one another. All right. And so now we're back to the same situation we were in before, where we've got where we have a set of vertical angles at a point here, because again, these are vertical angles that are obviously that are going to be equal to each other because they're formed by two intersecting lines at a point. So these angles do share a vertex, but they don't share a side. And so that means that these two are always going to be equal. And if these two are always going to be equal, that means that angle C is going to be congruent to angle C. If we have to be trivial with the shared side, we have to be trivial with the shared angles as well. So in this case, are they congruent? Yes. Congruency statement. I'm going to say again, triangle ABC is congruent to triangle, yeah, DEC. Almost wrote DEF there. By angle side angle. So that is how we go about proving that one. And when you actually start choosing how to use these and having the resources to choose them, generally the problem itself will kind of push you towards using a particular theorem or using a particular proof in order to solve the problem. You're rarely going to get a problem where you have all three sides, all three angles, and then the problem will say prove that these two are similar. Um, and then they say, prove that these two are similar or congruent. And you're like, well, I mean, they have the same size, they have the same angle yet. And you have to prove it using something other than the, well, isn't it obvious principle. So yeah, just try to keep these different theorems in mind, because whatever you're given as part of the question is generally going to be how you solve the question, because they're trying to test to see if you recognize it's problem recognition is what it is. If you can recognize if you can recognize what to use to solve a problem. All right. So here we have determine if the shapes are congruent. All right. So I've got one angle that is congruent to another angle. So I got to be a bit more precise with these angles. So I've got angle TSU. That's going to be congruent to angle RSU. Then for the side, I've got side SU congruent to side SU. And then finally, I've got angle RUS congruent to angle TUS. And again, do I have to list them in that order? Do I have to list them with that sort of priority? No, you don't. I just chose to do it out of, I don't know, boredom. But yeah, I just chose to do it that way arbitrarily. So are they congruent? Yes. And the congruency statement, I'm going to say triangle RSU is congruent to triangle TSU by, that's right, angle side angle. Had a brain melt moment for a second, because I was like, wait a second, how did I prove this? And so it was, yeah. All right. So the next one is the angle side. So I mean, angle side. It should be. I'm not going to read through the theorem. You can kind of read through that on your own. But yeah, if we have two angles and then a side, then they're congruent. I mean, that's pretty much, and that's pretty much it. I mean, the names of these aren't very creative. They're the big hint of how you're going to use them is it's pretty much in the name. It's pretty much in the name. So if angle A is congruent to angle D, if angle B is congruent to angle E, and if BC is congruent to EF, then triangle ABC is once again congruent to triangle DEF. And like I said, I mean, really at this point, we should probably just assume that anytime you have triangle ABC and DEF, that they're just going to be congruent or similar or whatever you're trying to prove at that point. So we're going to move on to our proofs to demonstrate that that the theorem actually does work here. All right, so we're going to determine if the triangles are congruent. So I've got two angles and a shared side. Okay, so if you're ever this is a good example of a problem where you're just given two angles. And so you're just given two angles, and technically you're given all three, right? Because I've got this first one, which is angle M. I've got the second one, angle J. But now I know that this third one is also equal to this. So the issue is that, so this is one of those, I mean, I mentioned earlier, it's about problem recognition and looking at what they give you and looking at what the information that's available and being able to recognize that the problem that they're giving you has all the information that you need to answer the question, but you can't but you have to make sure that you're answering the question that they want you to answer. There was a handout that we gave earlier today, just to kind of give you a hint as to when I'm recording this, where you were solving for x, and x was part of the solution, but the answer to the question was required that you take x and plug it back into a formula in order to solve for the side of a shape. And if you didn't do that, you wouldn't know it, or you would get a wrong. It wouldn't give you a wrong answer, but it would take you to a different location. Long story, but you would need to, it would just give you it'd take you down the wrong path. I think that's the best way to put it. And so I look at this and I think, if I confuse similarity with congruence, I look at that and I'm like, well, I've got one angle equal or congruent. I've got a second angle equal or congruent. Then if those two are equal, then because all three of them have to add up to 180 and the first two are equal, then that means the third one has to be equal, which is 100% correct. And if all three of the angles are equal, doesn't that mean they are congruent? And again, this comes down to problem recognition. If all three of the angles are equal, that does not mean that they are congruent. It means that they are similar. Congruent is different enough from similarity that saying that something is similar based only on what the angle measurements are is a major failure of concept differentiating between the two. So that's why you have to include a side element. And I don't mean like another, like like you have all the elements and then one more off, like, a bread course or a soup course or another salad. I mean like a side element as in part of the triangle. You have to include part of the triangle as part of the proof as well. And so with this one, as I mentioned, I look at it and I see potentially someone seeing it and saying, well, they're congruent because all three of their angles match up. Again, that's not congruency, that's similarity. So in order to determine if the triangles are congruent, what you have to look at and what you have to see, I see two angles and then a shared side. So again, two angles and a shared side, that tells me angle, angle, side. So I have angle JMK congruent to that's what it is, LKM. And to make sure my references were okay. So that's JL. Hmm. Hmm. Oh yeah, that's right, because I'm doing the number one. Okay, okay. My hand. You know what? This was throwing me off, so I'm just gonna. This one was throwing me off, so I'm just gonna get rid of it. Again, when you're doing the similarity statements, you have to make sure that you're referring to the same angle, and that the correct angles are referred to when you're doing the similarity statement as when you're doing the congruency statements. So let's see. So if JMK is equal to okay, so now if KJM is congruent to angle, and then I'll say MLK. So I'm starting with no measurement going to 2 and then to 1, no measurement going to 2 going to 1. Again, using the measured angles as reference points. And then finally, as ever, MK congruent to MK. Are they congruent? Yes. And now the congruency statement, which is just as tricky. I'm going to say MJK. There we go. Is congruent to triangle. And I'm just going to go angle 1, angle 2, nothing, to KLM. Triangle KLM by angle, angle, side. And there we go. All right. Next one, we have to determine if the triangles are congruent. I like our odds. Let's see. Well, yeah, yep. Okay. All right. Oh, this is okay. All right. Okay. Um, this one is. This one's. I'm not going to say it's mean, but it's it. As far as like again, talking about problem recognition, it's giving you more information than you need. And the issue with more information than you need is it's meant as a distraction. And so in this case, I would say we're supposed to solve it using angle, angle, side. And so I'm looking at angle, angle, side. I would use angle A, reference angle 1, angle C, reference angle 2, and then side BC, and use that as the basis for my angle, angle, side proof. But I can also prove it using reference angle A, side AC, and then and then reference angle C with the two lines, and that's angle, side, angle. And so again, it's the reason I say that it's devious is because all we have to do is prove that it's congruent, but we've got two different ways to prove it. And if you're ever in this position, and you're definitely going to be at some point, especially with standardized tests, if you're ever in a position where you see a path towards two answers, always go for the fastest one. Always go for the fastest, simplest one. And so in this case, the fastest, simplest one is to go angle, angle, side, because you're in the angle, angle, side congruence theorem section of the textbook. So angle, angle, side. So I've got angle A. If angle A is congruent to angle C, if angle C is congruent to angle A. If they want to be confusing, I can be confusing. And then if BC is congruent to AD. It is congruent, and I'm going to say um, nothing to 1 to 2, so triangle BAC is congruent to triangle DCA. Oops. And then by angle side. And again, like I said, could you prove this using angle side angle? Easily, without any question. But this is the angle side congruency theorem section. So I would just focus on the easiest possible answer, the most direct answer, and then just basically go from there. All right, we've got one more theorem. This one's actually new to me. Oh, here we are. This one's actually new to me. I never actually had this theorem, but it's kind of intuitive. Never actually had to deal with this theorem. I don't want to say that it's, I mean, it is new to me. I actually have never heard of this one or used it before. So, hypotenuse leg congruency theorem. So, if you have so if the hypotenuse or the leg opposite a 90-degree angle, that is what the hypotenuse is. It's a very specific term for triangles, where it's the side of the triangle that's opposite a right angle. So if the hypotenuse and the leg of and there are of two triangles are congruent, then the two triangles are congruent. It's basically I mean, it's kind of an offshoot of the side one, in that, like, anyway, I'm not going to get into it. So if BC is congruent to EF and AB is congruent to DE, then triangle, ABC is congruent to triangle DEF, and there we go. We've done it again. All right. Determine if the triangles are congruent. Well, we've got right triangles, and thankfully, we only have to prove two things. Let's see. The first thing we have to do is we have to show that okay, if you're going to use a theorem that requires another condition to be met. So with most of the theorems that we've had, and with theorems that we've had so far, with angle, side, angle, angle, side, side, etc., those worked with pretty much any triangle. Those worked with every triangle. It didn't matter what the shape was. If you were a triangle and you existed and you had angles and you had sides, then these rules would apply to you as far as congruency was concerned. So for the hypotenuse leg, I think this is why no one ever taught it to me. For the hypotenuse leg congruence theorem with the triangle, the hypotenuse leg theorem only works if the two triangles are right triangles. So if they're both scalene triangles, there is no hypotenuse, because the hypotenuse is opposite the right angle. If the two triangles are acute triangles, again, no hypotenuse. If it's an obtuse triangle or an isosceles triangle, again, no right angle, and so no hypotenuse. So another condition that you would have to establish when you're doing this congruence theorem is you would have to establish that the two triangles that you're working with are right triangles. And I'm not saying it's a difficult thing to prove. I'm not saying it's a difficult thing to establish, but you do have to establish it before you can use the theorem. Because if you try to get away with using the theorem on an equilateral triangle, it's not going to work out. So let's see. Determine if the triangles are congruent. So I'm going to say ACB, triangle ACB. and triangle, and triangle ZYX are, I'll just say they're right triangle, are just right triangles. I'm not sure how to notate that really, or how to shorten it, but that's but that's the best I can do. That's the best I can think of for right now. So now that we've established that they're right triangles, AB is congruent to ZX, and then CB is congruent to XY. So are these two triangles congruent? Yes. So what is the congruency statement? Congruency statement is triangle using the right angle as a reference. ACB is congruent to triangle ZYX by HL. And again, in order to use the HL theorem, you have to establish the right angle the nature of the right angle. All right. Next one. Looks like we've got an isosceles triangle that we dropped the altitude on. If you dropped an altitude, if you remember from our similarity unit, that's basically you take a point from you basically take a point from the triangle, and you draw a line to the opposite side in such a way that it forms a 90-degree angle. So in this case, we actually have a well, all right. Determine if the triangles are congruent. So I dropped it down here, and I've got, well, I can say conclusively, triangle ADB, and triangle ADC are right triangles. Again, because I'm not sure what the nomenclature is for the statement. Let's see, I also know that AB is congruent to AC, and unfortunately, that's where it ends. There is no, yeah, that's where it ends, unfortunately. Wait. So, well, see, here's the problem. What I'm trying to do is I'm trying to justify saying that AD is an angle bisector. Because if it's an angle bisector, then that means that BD and DC are equal parts. Are equal parts. Um, hmm. That's the problem. I'm trying to. I think there's a proof in Euclid's Elements where if you drop the altitude of an isosceles triangle, that the resulting intersection bisects the base, bisects the opposite base. That sounds right, but the thing that bothers me is that if they did that, or if that was the case, um, wouldn't they have notated that, or wouldn't they have written that on the diagram? Wouldn't that have been something that they would have notated on the, like I said, wouldn't that have been something that they notate on the drawing? Um, yeah, this one's a little bit tricky, because the thing is the part that's getting me is because it's an isosceles triangle, I know that the two angles to the left and the right are going to be equal to one another. So if they're going to be equal to each other, then that means that whatever the top angle is, well, that's the thing though. Just because they're equal to each other doesn't mean that I know where the altitude is going to drop, or, well, I kind of do, but does it bisect? But Yeah, I don't have any proof that it's an angle bisector, though. Hmm. So I went ahead and looked it up on Euclid's Elements, and it actually is a theorem, which, I mean, I'm certainly glad that they're referencing Euclid's Elements, but I think it's kind of a dirty trick that you have to reference Euclid's Elements in order to answer a question to prove a theorem. So it turns out I was right. If you drop the altitude from a isosceles triangle, not only does it bisect the angle that you're dropping it from, but it also bisects the base that it intersects with. So BD and DC are in fact equal to each other. But again, if that's the case, why not just include the two hash marks? I mean, it's not like they ran out of space or anything. Anyway, that is the case. Like I said, I'm a little irritated that we had to look up Euclid's Elements in order to solve in order to prove an example of a theorem from a workbook. But yeah, I mean, like I said, I didn't write this thing, so all right. So now that we know BD is congruent to DC, we know now that these two triangles are congruent. Congruency statement is triangle ADB is congruent to triangle ADC by HL. So there we go. So there are two non-examples of proofs. One of them is one that I mentioned earlier as far as similarity is concerned, and that's angle, angle, angle. The reason being that you can have all three of the angles be equal to one another, but the sides just be completely out of whack. And as long as they're proportionately the same, you can have the sides be just massively different from one another, and the angles will be unchanged. Angle, angle, angle is a proof of similarity, not a proof of congruence. And so angle, angle, angle isn't going to help you anything. Then there's the infamous angle side side theorem. It doesn't work. It never works. Every person in like every kid in geometry at some point has tried to make it work because of the name. It it will not work. It doesn't work. It can't work. Please stop trying to make it work. Um, it stopped being funny in the 80s, and it's still not funny now. So please stop. All right, let's see if the triangles themselves are congruent. Well, I've got this angle is congruent. Well, if these angles are equal and these ones are equal, let's see, I've got an angle. So I have to determine if these angles are congruent. So C is a vertical angle. I've got A as a right triangle. So is there a way that I can show that these are congruent? Um, hmm. I just have, well, I I know that the angles are equal, but we basically just established knowing that the angles are knowing what the angles are doesn't help you. I know that C is equal to C, and then I know because this is 90 degrees, and I know what C is. I know what D is, and if C is the same and A is the same, then that means that D and B have to be the same. But that's the thing. I only know angles. That's all I know. I don't have any of the side information. And so in this case, uh, no, I can't. Um, I do not have enough information to say whether or not they are congruent. And it's not even an issue of small type or small print. The only information I have are angles. You need some kind of side measurement in order to be able to, yeah, in order to be able to make that declaration. All right, last one. Determine if the angles are congruent. All right. Um, Well, I think it's hard to make out, but I think I've got that. I think I've got those two there. And, oh, no, this isn't going to work. Um, if we were going to do side angle side, then it would have to be side, this angle, and then side. Um, if we're gonna, this is going to be angle side side. So this isn't going to work either. And here I thought it was going to be a genuine, like, let's see if you can make this work challenge. No, it's just an example of angle side side and angle angle angle. So anyway, this was a hopefully this goes a little bit faster in class, but this is a going over of the different theorems that we are going to use in order to prove congruency. Um, Again, once we know congruency and we can establish congruency, once we know congruency and we can establish congruency, then then we're in really good shape moving forward as far as triangle works go. And yeah, so I guess that's all we got to talk about for today.